So design of Chebyshev filter. So Chebyshev filter it has a magnitude response h of j omega is equal to a divided by 1 plus epsilon square cn square omega by omega c whole power 0.5, right? So this is the magnitude of your Chebyshev low pass filter. In this one, a is going to be the gain of your filter, and omega epsilon is going to be your constant, and your omega c is going to be your 3 dB cutoff frequency, and the Cn of x, so that is going to be the function. So this x is nothing but your omega by omega c, right? So if your value of your x is less than 1, omega by omega c value is less than 1, the Cn of x can be obtained by the formula cos of n into cos inverse of x, right? So suppose if your x value, that is your omega by omega c value, is greater than 1, then your Cn of x can be obtained by cos h of n cos h inverse x, right? So this will give you your Cn of x, right? So here this is going to be the response here, frequency response here. So here you have your equiripple in your passband. Okay, so the equiripple, either the equiripple will be there in your passband or your stop band, right? So here, based upon this one, you have two different types of your Chebyshev filter, kind 1 and kind 2, right? So here, normally, how this equiripple will be now? The equiripple, you have your magnitude will oscillate in between your 1 and square root of 1 divided by 1 plus epsilon square, that is 1 to 0.77707, it will get oscillated, right? So that is called as an equiripple in passband, right? Sometimes what happens, the same equiripple will be present in your stop band. Okay, so based upon this, you have two Chebyshev filter types here. Type 1 is your first kind, type 2 is going to be your second kind. So if your equiripple is placed in your passband and maximally flat stop band, it's going to be your kind 1, right? If your maximally flat passband and equiripple stop band, if you have your equiripple in your stop band, it is called as a kind 2. So normally we will be using with your kind 1, right? So now we are going to design your kind 1 too, right? So here the Chebyshev type 1 filter are all pole design here. Okay, so here the magnitude response approaches the ideal response when your value of your n gets increases. If you're going on increasing your n value, you just see you'll be getting your close to your ideal response. So it's your n equal to 2, n equal to 4, n equal to 5. While increasing your n, it reaches to your ideal response here, right? So this is about your Chebyshev filter. Now we can see the steps for your Chebyshev filter here, right? So here step-by-step procedure here, what are all the parameters here you are going to use is your AP less than or equal to modulus of h of j omega less than or equal to 1.0 or 0 less than or equal to omega less than or equal to omega pi, and then modulus of h of j omega less than or equal to as, where omega s less than or equal to omega less than or equal to pi. So your omega p is nothing but your passband digital frequency, your omega s is your stop band digital frequency, your omega p is passband analog frequency, and this is your stop band analog frequency. AP is gain at your passband, and your AS is gain at stop band. Alpha p is passband attenuation and your stop band attenuation. And your T is obtained by 1 by Fs, which is nothing but your Fs is nothing but your sampling frequency. So the step to design your Chebyshev filter is, first step is going to be you calculate your omega p and omega s. So here, based upon your technique, they ask you to solve. We are going to have your formula, right? So for your bilinear transformation, your omega is obtained by 2 by t tan omega by 2, and for your impulse invariant, it's going to be omega p. So omega is obtained by omega t here, right? And step 2 is to calculate your order of your filter. So the order of your filter can be calculated by n greater than or equal to cos h inverse of 1 by as square minus 1 divided by 1 by ap square minus 1 whole power 1 by 2 divided by cos h inverse of omega s by omega p. So this is a formula here. Here also the n will be whatever the n we obtain, and n will be equated to the next nearest next largest value here, right? Next is your step 3. Step 3 is to get your cutoff frequency. Here in Chebyshev filter, your cutoff frequency is nothing but it's equal to your omega p. So we are not going to find it, whatever the omega p we have obtained. So it will be considered as a cutoff frequency here. Step 4 is to determine your normalized transfer function of your analog filter. So here the formula you have for even, you have your formula, for odd you have your formula. For n is even, your h of s is nothing but this is pi. Pi k equal to 1 to n by 2. That is your product of sum is equal to bk divided by s square plus small bk sn plus ck. Right? And your odd for n is equal to odd, it is nothing but b naught divided by sn plus c naught, pi k equal to 1 to n minus 1 by 2 bk divided by s square plus bk sn plus your ck. Now we have to find the formula for finding your capital Bk, small bk, and then your capital B naught, small c, capital C naught, and then your ck. So the formula for finding it is your C naught is equal to your y suffix n, where n is nothing but your order of your filter. The y of n is given by 1 by 2 epsilon of your 1 plus epsilon square plus 1 whole power 1 by 2 and plus 1 by epsilon power 1 by n minus 1 by epsilon square plus 1 power 1 by 2 plus 1 by epsilon power minus 1 by n. Right? So here the epsilon is obtained by the formula 1 divided by ap square minus 1 whole power 1 by 2. Right? So now if you substitute your epsilon value here in this formula, you will be able to get your y of n, and then if you are obtaining your y of n, then you can get your c naught. Right? Next, to find your ck. Right? So ck is nothing given by 1 y of n square plus cos square of 2k minus 1 pi by 2n. Your bk is given by 2 into y of n sine 2k minus 1 pi by 2n. Then for identifying your capital Bk, for n equal to even, you substitute your h of s. In h of s, you substitute it as a 0 here as s, and that value should be equated to 1 divided by 1 plus epsilon square power 1 by 2. For n equal to odd, so you just substitute your h of s, replace your s by 0 and get your h of 0, equate it to 1, so that you'll be able to get your bk here, right? So by getting your c naught, ck, bk, and then your capital bk, so you'll be able to get your step 4, that is your h of s, which is nothing but your normalized transfer function. Now step 5 is to determine your unnormalized transfer function h of s by choosing your appropriate type of filter. And step 6 is determine your digital transfer function h of z using your chosen transformation. And step 5 is realize the transformation h of z by a suitable structure. If they ask you to realize it in terms of your structure in your question, you have to go for your step 5. Else, you can start putting your step 6. So this is about your procedure, step-by-step procedure of your Chebyshev filter.
Let's see the problem here. Design a digital Chebyshev low-pass filter for the desired specification using impulse invariant technique for 0.8 less than or equal to modulus of h of j omega less than or equal to 0 less than or equal to omega less than or equal to 0.2 pi. And modulus of h of omega less than or equal to 0.2 or 0.65 less than or equal to omega less than or equal to pi. So first we have to get the 5 parameters from the problem statement here. So the 5 parameters are AP, AS, omega P, omega S and T. So your AP is going to be your 0.8, AS is going to be 0.2, omega P is 0.2 pi and omega S is 0.65. And since they didn't give anything about your T, you can consider your T as 1 sec. And here they ask you to design Chebyshev low pass filter. So using your impulse invariant technique. So step 1 is to determine your omega p and omega s. So since they ask you to solve using your impulse invariant technique, your formula is omega equal to omega by t. So by substituting your omega value as 2 pi to 0.2 pi and 0.6 pi, you'll be obtaining your omega p, analog omega p and omega s as 0.6283 radian per second and 1.8849 radian per second. Steps 2 is to get your order of the filter. For Chebyshev filter, the order of your filter is given by uh, uh, n is greater than or equal to cos h inverse of 1 by a square minus 1 divided by 1 by ap square minus 1 whole power 1 by 2 divided by cos h inverse of your omega s by omega p. So by substituting the value of your as, ap, omega s and omega p, so you'll be getting your values here. So take your calculator. Calculator should be in radian mode. So hyperbolic function can be obtained by pressing your button HYP and shift cos. If you press, you'll be getting your cos H inverse. If you want, you can try hyperbolic button plus shift cos. So you'll be getting your cos H inverse, right? So you can type it as such. So cos H inverse of open bracket, again one open bracket, 1 divided by zero point 0.2 square inverse minus 1 close bracket divided by open bracket zero point 0.8 square inverse minus 1 close bracket, again one close bracket, 1 by 2 power 1 by 2 close bracket divided by cos h inverse of open bracket 1.8849 divided by 0.6283 close bracket equal to. So I repeat, cos h inverse of open bracket, again one open bracket, again one open bracket. So three open brackets, 0.2 square inverse minus 1 close bracket, open bracket, point divided by open bracket zero point 0.8 square inverse minus 1 close bracket, again one close bracket, power 1 by 2, again one close bracket, divided by cos h inverse of 1.8849 divided by 0.6283 close bracket. So if we press equal to, you'll get your value was 1.4545. So your n value will be next largest integer, that is n equal to. Step 3 is to determine your omega c. Here in Chebyshev filter, omega c is equal to your omega p. So your omega c is equal to 0.6283 radian per second. Step 4 is to determine your normalized transfer function of your Randolph filter. So since n is equal to 2, that is even, your h of s is equal to product of sum k equal to 1 to n by 2 bk divided by s square plus small bk s plus k ck. So your n is equal to 2, so 2 by 2 is going to be 1. So your h of s is equal to b1 divided by s square plus small b1 s plus c1. So now we have to find the value of your capital B1, small b1 and then c1. So the formula for your small bk is 2yn sine 2k minus 1 by pi by 2n. So here k value is equal to 1. So replace your k as 1 here. So 2 into yn is your 2. Sine 2 minus 1 pi divided by 4. So to calculate this one, you need your y2. Y2 first of all. So for CK also, if you substitute the value, you need your Y2. So to calculate your BK, B1, C1, you need your YN. So you'll find your YN here. The formula for it is 1 by 2 of 1 by epsilon square plus 1 power 1 by 2 plus 1 by epsilon whole power 1 by n minus 1 by epsilon square plus 1 whole power 1 by 2 plus 1 by epsilon whole power minus 1 by n. So here this bracket, the value inside the bracket 1 by epsilon square plus 1 power 1 by 2 plus 1 by epsilon. So this value is going to be common for both. So that value power 1 by 2 minus the value power minus 1 by 2. So now we'll be finding your epsilon value. So 1 by ap square minus 1 whole power 1 by 2, which is equal to 1 by 0.8 square minus 1 power 1 by 2. So open bracket 0.8 square inverse minus 1 close bracket power 2 inverse. So the value will be 0.75. So now y2 is equal to 1 by 2, 0.7 square inverse plus 1 by the whole power 1 by 2 plus 1 by 0.5 whole power 1 by 2 because n value is 2. Now just calculate the value inside your bracket here. So square open bracket 0.75 square inverse plus 1 close bracket power 0.2 zero point 0.5 plus 0.75 inverse equal to, I repeat, open bracket 0.75 square inverse plus 1 close bracket power 2 inverse plus 0.75 inverse. The value will become 3. So 1 by 2, 3 power 1 by 2 minus 3 power minus 1 by 2. So it is 2 inverse into open bracket 3 power 2 inverse minus 3 power minus 2 inverse close bracket. The value will be 0.773. So your CK value is obtained by y2 square. So 0.773 square plus here cos square of pi by 4. So pi cos pi by 4 whole square, the meaning here. So the value is 0.8333. Now you can calculate your B1. So B1 is 2y2 sine pi by 4. So 2 into your y2 is going to be 0.773 into sine pi by 4. The value is 0.8164. So now your C1 value we have found out your C1 and B1. So the left out is going to be your capital B1. So for n equal to 1, your capital B K can be identified or calculated using h of 0 should be equated to 1 by epsilon square power 1 by 2. So h of 0, h of s is b1 divided by s square plus b1 plus c, b1s plus c1. If you substitute your s as 0, then what happens? The left out is b1 divided by your c1. So your b1 divided by c1 should be equated to 1 divided by 1 plus epsilon square power 1 by 2. So one b1 is nothing but just take your c1 here. So c1 divided by 1 by epsilon square power 1 by 2. So c1 is 0.8333 divided by 1 plus 0.75 square power 1 by 2. So 0.8333 divided by open bracket 1 plus 0.75 square close bracket power 2 inverse. So the value is 0.6667. So now all the three values have been found out. B1, small b1, c1, capital B1. Where h of s is nothing but b1 divided by s square plus b1s plus c. So substitute your is 0.1667. S square plus small b1 is 0.8164 s plus 0.8333. So your normalized function, transfer function h of s is equal to this one. So your step 4 is to get your unnormalized transfer function, choosing your appropriate type of filter. Here they ask you to design your low pass filter. So your in your h of s, your s should be replaced by s by omega c. Omega c here, you just solve this equation by taking your omega c square as a LCM and denominator will be numerator. So 0.667 omega c square divided by s square plus 0.8164 into omega c s plus 0.833 omega c square. So the omega c your normalized transfer function is 0.2632 divided by s square plus 0.5129 s plus 0.3289. The step 6 is to find your transfer function, digital transfer function using the chosen transformation. Here they ask you to use your impulse invariant technique. So h of s is equal to this one. So we have to check whether the denominator can be factorized or not. So here this function denominator cannot be factorized. So the possibility is either it will be of s plus a divided by s plus a whole square plus b square or b divided by s plus a whole square plus b square. Since your numerator doesn't have your s, so the possibility one and one possibility is b divided by s plus a whole square plus b square. For that only we have the formula. So you have to make this function 1 divided by s square plus 0.5129 s plus 0.3289 should be equated to 1 divided by s plus a whole square plus b square. So equate the denominator and then expand the side and equate your coefficient of s. So 2a equal to 0.5129. So a is equal to 0.2564. Now equate your constant a square plus b square equal to 0.32. B square equal to 0.3289 minus a square. So substitute your a value. So your b square is 0.2631. So b is equal to 0.5130. So now I found your value of a and b. So I can write this 0.2632 divided by s square plus 0.5129 s plus 0.3289 as your 0.2632 divided by s plus a whole square plus b square. Now we have to substitute the formula here. So s plus a, that is your b divided by s plus a whole square plus b square. The b value is 0.5130, but the numerator we have some other value. So multiply and divide the numerator by 0.5130 so that the value of your function transfer function will not be changed. So now what happens here? I'll be a into b by c can be written as a by c into b. So 0.62632 divided by 0.1530 into this one. So this one is nothing but 0.5131. So now b divided by s plus a whole square plus b square. Now we can substitute your formula. So by substituting your value of your A as 0.2564, B as 0.5130 and T as 1, so you'll be getting your answers here. So the calculator should be in radian mode. So e power minus 0.2562 into sine of 0.5130 into z inverse, that is 0.7738 into 0.4908 z inverse, divided by 2 into e power minus 0.2564 into cos of 0.5130. The value is 1.3484. E power minus 2 into 0.2564 is 0.5988. So now the value of this value b divided by s plus a whole square plus b square is this one. So now it should be multiplied by the coefficient of 0.5131. So if I multiply, your h of z is nothing but 0.2632 z inverse divided by 1 minus 1.3484 z inverse plus 0.5988 z power minus 2. Thus, I have designed your digital Chebyshev low pass filter using the impulse invariant technique for the given specifications. Now we'll solve one more problem in your bilinear using your bilinear technique. To design a digital Chebyshev low pass filter for the desired specification using your bilinear transformation. So here the value was given here. So first you have to get your 5 parameters AS, AP, omega P, omega S and T. After obtaining that 5 parameters, you have to calculate your step 1, that is your omega P and omega S. So since it is a bilinear transformation, they ask you to use the formula is 2 by T tan omega by 2. So by substituting your omega value, you'll be able to get your analog omega P and omega S as 0.6949, 0.649 and 1.099 radian per second. So step 2 is to get your order of your filter. So formula is cos h inverse of 1 by a square minus 1 divided by 1 by ap square minus 1 power 1 by 2 divided by cos h inverse of omega s divided by omega p. So substituting your as, ap, omega s and omega p, you just using your calculator, cos h inverse open bracket, again on open bracket, again on open bracket, 0.2 square inverse minus 1 close bracket divided by open bracket 0.82 square inverse minus 1 close bracket, again 1 close bracket, power point, that is 2 inverse close bracket divided by cos h inverse of open bracket 1.099 divided by 0.649 close bracket. If you press equal to, your n value is 2.293. So your n is equal to largest integer. Step 3 is to calculate omega c, which is equal to your omega p in your Chebyshev filter. And step 4 is to determine the normalized transfer function of the analog filter. So n is odd, so your h of s is equal to b naught divided by s plus c naught, product of sum k equal to 1 to n minus 1 by 2 bk divided by s square plus bk s plus ck. So So here n minus 1, 3 minus 1 by 2 is going to be 1. So your b naught s plus c naught into b1 divided by s square plus b1 s n. That's your c1. You have to find your value of b naught b1, c naught c1, small b1. Your b1, this is the formula for finding your bk ck. You have to find your y of yn. So for that you need your epsilon. So epsilon is 1 by ap square minus 1 whole power 1 by 2. Where epsilon is going to be 0.75. Now find your y3. So y3 is equal to 1 by 2 of this formula. So substitute your epsilon square value, epsilon value. So find the value of this term 0.75 square inverse plus 1 close bracket power 2 inverse plus 0.75 inverse. So the value will be 3. So 1 by 2 into 3 power 1 by 3 minus 3 power minus 1 by 3. So 1 by 2, that is 2 inverse into open bracket 3 power 3 inverse minus 3 power minus 3 inverse close bracket. So your y is equal to y3 is equal to 0.34374. So substitute your c naught will be equal to your y3, which is nothing but 0.374. Find your b1 and c1. So c1 is equal to formula is y3 square plus cos square of pi by 6. So 0.374 square plus cos open bracket pi by 6 close bracket square. So C1 is 0.89. Again, substitute your value of K as 1 and get your B1. So 2 into Yn into sine pi by 6. So it is 0.374. So your H is equal to B naught B1 divided by S plus C naught. Substituted S square plus B1 small b1 plus C1. So now have to find your value of B naught B1. If n is odd, that B naught B1 value can be obtained by h of s substituting your value of 0 and equate it to 1. So if I substitute this value of s as 0, the left out value is b naught b1 divided by 0.374 into 0.89. So which is to be equated 1. So your b naught b1 is equal to 0.33. So you can substitute your b naught. So in the numerator you'll have your b naught b1. So b naught b1 is equal to 0.33 divided by s plus 0.374 into s square plus 0.374 s plus 0.89. So step 5 is to determine your unnormalized transfer function. So here they ask you to find your low pass filter. So replace your s by omega c. You'll be getting your value here. So you just solve this expression. Take your denominator LCM for the denominator omega c cube. The denominator's denominator will be numerator. Substitute your omega c value. So you'll be getting your unnormalized transfer function. Step 6 is to determine your digital transfer function h of z using your transfer choose and transformation. So replace your s by 2 by t 1 minus z inverse divided by 1 plus z inverse in your h of s. You'll be getting your h of z. Now solve this expression. Take your denominator and then LCM for the denominator, and then denominator will be numerator, and in the denominator the value first. So take the value of h of z. So here in this term 2.243 common out. Here it is 4.86 common out. So you will get your h of z as 0.0083 into 1 plus z inverse whole power 3 1.49 z inverse plus 0.183 z power minus 2. So this is how the digital filter has been designed. Digital Chebyshev filter has been designed using bilinear transformation. Suppose if they ask you to design your analog Chebyshev filter, so directly the step 1 is to find your order of the filter. Step 2 is to find the cutoff frequency. Step 3 is to find your normalized transfer function, and step 4 is to find your unnormalized transfer function. So you'll be getting your H of S. So this is the design procedure for your analog Chebyshev filter. For further clarifications, log into edilo.blogspot.com. Thank you, students. We'll meet in the next presentation.